Hi, my name is Dr. Barry Flannery. I'm the founder and CEO here at Xerotech. Welcome to another episode of XD Tech Talks. Today we're going to be talking about safety in battery electric systems, its importance, and what it means from cell level all the way through to pack level. So let's get started. So let's talk about some real practical safety considerations in battery pack, battery module safety engineering, and the features that you'd expect from a battery pack or a battery module. From a battery cell perspective, back to our individual cell, there's basic things it doesn't like. It doesn't like over or under voltage. It doesn't like over or under temperature. And it doesn't like over current. Each of these are different. So when we look at voltage, over voltage for the vast majority of chemistries is more than 4.2 volts. Or for LFP, it's over, say, 3.65 volts, above their charge limits. This is really, really bad to overcharge a battery. It can result in irreversible electrochemical damage. It can result in excessive heating, gas generation, fire, many other factors. Big no-no in terms of overcharging of battery cells. So that's a critical one to do. And for most chemistries, when you go below 2.5 volts, also very bad. So with a battery cell, 0 volts is not zero. Something is totally wrong if you've managed to achieve 0 volts in a battery. The laws of physics between the different electrochemistry parts of a battery mean that 0 is actually 2.5 volts. So when the battery is actually reading 0 volts, that means it's under a small bit of load pulling it down below the 2.5 volts. But when you're below 2.5 volts, you're causing irreversible electrochemical damage to the battery cells. This won't result in a fire risk, but it will result in an irreversible capacity loss. And where you can run into danger and difficulty is recharging a battery cell that has been deeply discharged. That could lead to certain fire risks like dendrite growth, which are basically Christmas trees that grow from one side of the battery to the other through the separator, creating an internal short circuit. So voltage protection is incredibly important. And that actually is one of the things that a CMU or a cell management unit or a slave BMS does on a battery module. It's monitoring voltage, and it also does a little bit of housekeeping when it comes to voltage, but we'll come back to that. The next piece when it comes to a module is over temperature and under temperature. So the big risk comes with, if you make a battery cell too hot, it can go into thermal runaway, or it can start to continue to increase in temperature, resulting in potentially a fire. But in general, when the batteries are warm, above 30, 40, 50 degrees Celsius, they're under accelerated aging. They are degrading much faster. There's good chemical reactions and bad chemical reactions. The good ones are the ones that power your vehicles. The bad ones are the ones that degrade lifetime. Unfortunately, the hotter the battery cell, the chemical reaction rates increase exponentially. The good ones and the bad ones. So high temperature is not always a good thing to have. When it comes to under temperature, below 0 degrees Celsius, recharging most conventional chemistries can result in irreversible damage due to cell potentials and lithium plating and many other factors. So measuring temperature is important. So greater than 60 degrees C and less than 0 degrees C are areas you want to be careful in. So basically, you need to measure voltage and you need to measure temperature. When it comes to a current perspective, it's very important that you don't over discharge a battery cell, because what can happen there is every source of energy has an internal resistance, which means that when you pull current out of it, its voltage will dip. It'll have a voltage drop. And that's a function of how much current you pull out. So if you pull an excessive amount of current, what you'll actually do is you'll pull the terminal voltages below your under voltage cutout. Similarly, for charging, you'll do the exact inverse. If you overcharge too aggressively, you'll breach the upper limit. So you've got to be careful with that current measurement. When it comes to battery modules, we measure the voltage and the temperature at a module level. So for example, in a Xerotech module, but virtually every other battery module, they might have a battery management system here that's measuring the voltage of each cell group. An important thing to understand is that you don't have to measure each individual cell. You only have to measure all the same cells in a string. And what that means is, if we've got a bunch of different battery cells here on different groups, what matters is the bus bar, because if they are electrically connected on the same bus bar, they're all at the same voltage. So for example, on this module, you would need a voltage sense point touching this bus bar, this one, and obviously the corresponding ones on the opposite side, because every single battery cell that's on this bus bar is all at exactly the same voltage. So you only need to measure the bus bar. From a temperature perspective, it's obviously impractical to measure every cell in the pack. So typically you measure a couple of different sensors at a couple of different points. Some manufacturers might only use 1 or 2 sensors per module, or maybe even 1, depending on. So in a Xerotech module, just because it's in front of us here, we measure 4 points on one side of the module. That's on the coolant exit side of the module. So basically it will be the hottest or the coldest point on the module. The last cell at the end of the module on the exit is where we measure. There's different control strategies depending on what you are trying to achieve. Some differences between the two, but in general, all are acceptable. The final piece in relation to current is virtually no manufacturers will measure current at a module level. It doesn't make a lot of sense. You could infer this through voltage drop, but that's usually done at your main battery management system, your system level, what we call our BDU, or battery disconnect unit, through a current sensor, a current shunt. So you've got to look at these from a safety perspective. It's very important. These are the main things you can control. And what's interesting to point out, for a module, it actually has no control over any of these things. All it can do is measure it. One thing a module does do is ensuring that the buses, each one's here, are in balance with each other. So if we've got our module here with different cell banks that are all in parallel, the voltage here could be 3.701. The one here could be 3.765, and this could be 3.799. You want to try and make sure that these are all balanced with each other within some threshold. A typical threshold might be, 20 millivolts will be an acceptable threshold for balance. Lower is better. So what we do in most cases is we have balancing circuits that can be either active or passive. So the vast majority of the world uses passive balancing, which is basically you have a small resistor on your BMS board that turns on and it burns off the heat, burns off the excess energy as heat. Active balancing is a bit better, not actually for efficiency reasons, although that's a nice help, but for power transfer. You're limited in the amount of power that you can burn here to usually about a watt for most battery systems, whereas active systems, they can shuttle energy from one bus to another. So you're actually discharging one bank and charging another, but also the amount of power that can be transferred is much, much higher. It'd be several watts or even tens of watts, if not hundreds of watts. So active balancing is nice in that regard, but it adds a lot of cost and complexity. So that's virtually what every single BMS on a module level is doing. It's measuring voltage and temperature, and it's doing balancing. So that's safety at a module level to avoid these critical issues with the cells. So if you keep a cell within its voltage limits, within its temperature limits, it's generally going to be okay. And it goes without saying that you're not over discharging or overcharging the battery cells. So from a battery pack perspective, we look at a number of different features again. The current is most appropriately done at a pack level through the main control box, through a current sensor. But we also look at other factors like isolation, and also the HVIL circuit. There's a couple of other, depending on suppliers, things that people might look at. People might look at shock, vibration, crash, humidity, depending on. There are other features at a pack level, but the most important one is very much the current, that you don't want to be over discharging a battery module or a battery pack or even a battery cell. So the way we do this in most systems is we're measuring this number of different ways. It could be with a shunt or a Hall sensor. So that's basically a lump of copper that we pass current through. It's a little bit of a voltage drop on it. So you measure the voltage drop with a known resistance, it tells you the current. Or a Hall sensor is you pass current through a magnetic loop and it generates a voltage that you can measure and infer the current from that. So you may have heard statements like ASIL levels, automotive safety integrity levels, that there's an ASIL B or an ASIL C or an ASIL D system. A lot of that relates to system design for functional safety, but on a practical basis, one of the things it influences is having multiple ways of measuring things, because if one fails, you want to have this redundancy. So in our BDUs, or most BDUs, they'll be measuring the current and they'll probably have two independent current sensors reading the same thing. And then also an important thing that we look at is isolation. So with a battery, it's got a plus and a minus, high voltage plus, high voltage minus. Both of these are floating with respect to the chassis or ground. It's different to the power in a building. So what isolation is doing is it's checking between HV plus, HV minus, and ground. It's making sure that the resistance between these two things is high. You want to make sure it's above a certain threshold. And depending on the standard, you're looking at about 100 ohms to 500 ohms per volt. So basically, you need to be a few 100,000 ohms of resistance between each of these for your system to be good. So there's special sense circuits happening inside of that BDU or in other system packs, measuring between HV plus and ground, HV minus and ground, to ensure we have isolation. One of the other most important things we have in a pack is the HVIL circuit. So the HVIL means high voltage interlock loop. So on the packs behind me here, you'll see a lot of orange connectors. Every one of those orange connectors has something called a HVIL loop inside of it, the high voltage interlock loop. And what that does is, in any connector, you've got heavy power connectors that are basically connecting from one side into basically a socket on the other side. And what you want to do here is to make sure that you don't, when you open this back, you do not want to open this under load, because what will happen is you'll get a spark. As those two surfaces get very close together, the voltage difference between them will be whatever the voltage of the pack could be. It could be a few hundred volts. And with a millimeter of air, it could spark across. Or worse yet, it's not really on making, but mainly breaking the current. It could spark and then hold a plasma and actually hold a much larger gap that's being incredibly destructive and damaging to the contacts and can also present a fire risk. So with a connector design like this, they actually have a separate little sensor circuit that's a little set of pins that are going into another socket here. And these will be break first and make first pins. So that means that this will open slightly and it will send a signal to the controller that the connector has been opened, but it's still electrically connected with the main power connectors. So this sends a signal back to the BMS, which instantly opens the contactors or tells the system to stop drawing load to ensure we don't create an arc flash in our connectors. So HVIL is very important, that you do not ever, under any circumstances, break or open an orange connector under load. It will create a big spark and flash and will burn the connectors and can present a hazard to you. So battery systems will then emergency disconnect under load. But the problem is, this extremely destructive event that happens at the connectors that actually even happens in the contactors to do it. So you should never break contactors under load. You can only do it 1 or 2 times before the contactors need to be replaced. So that is an emergency disconnect power down. So the normal thing that happens in batteries is you get a HVIL loop fault, the BMS will immediately signal all other parts of the system, stop drawing load immediately. Hopefully they'll do that, and if they don't, within a few tens of milliseconds, the contactors are going to open then, potentially under load. And in relation to current and short circuits and other factors, we do also have further levels of protection with fuses. So we have active protection, that we can open the contactors under load, but that does cause a lot of damage to the contactors. We have mechanical fuses in some cases that will burn and blow and break the circuit. But in a Xerotech module, we also use cell level fuses. Every cell is wire bonded, which acts as an electrical fuse as well, a further third level of safety. Now, the other safety mechanisms that are within batteries in terms of active measurement, active protection systems, it varies from supplier to supplier. Some employ accelerometers that are looking at shock, vibration. These can be set at a threshold, so you can see a crash limit. If you see a G shock above a certain threshold, you say, looks like a crash. I'm going to open contactors. I'm going to blow the pyro fuse, whatever you might do. Or you might be looking at humidity and temperature at a system level and many other factors. It depends, but your core safety elements are voltage, temperature, current, and then looking at main breaks in isolation or breaking power conductors under load. When it comes to other system level safety measurements, this varies very widely from pack supplier to pack supplier. So we'll just take the case of a Xerotech battery. We do also monitor other factors, such as the pressure in the cooling system to determine if there's leaks or failures, and we use this for second and third level protection, also to infer other ways that the system is being used. And also we will be looking at pressures inside of the housing and gas sensing and other factors as well to be early indicators or detections of thermal runaway. So thermal runaway detection is very, very important, that if something occurs in a battery, you want to know what's happened. Oftentimes there's very little pack manufacturers can do after it's happened, but detecting it is the first step. So thermal runaway detection. And as part of multi-layered safety within our pack, for example, we have multiple different detection methods to see what happens. And then we'll have passive safety features starting at the module that, generally speaking, if a cell is to explode in a battery, we can contain it to a single or maybe 2 cells by the cooling system intentionally rupturing and flooding that fire in combination with a structural fire retardant foam that contains it into a fixed area. Then at pack level, we do, or even at module level, we have multiple other layers of fire protection and non-flammable materials. At a pack level, we have special vents that vent the explosive conductive gases out of the pack and further detections. So there's a multi-layered stage of dealing with thermal runaway in a system and a first responder approach after it has occurred. So we spoke about some of the things that you can do to a module or to a cell to damage it, but when it comes to a pack, from a safety perspective, you also need to look at that as well. So at a pack level, you have to look at the interfaces of the battery. So you've got the cooling system, you've got the mechanical system, the general enclosure, environmental stuff. So you want to always be looking at environmental, you want to look at the cooling system, and then just the general mechanical interfaces. So from an environmental perspective, temperature, if it's very hot, very cold, if you're exposed to water, dust, dewing points and fog and other things like that, you need to worry about this to make sure that we're not introducing moisture and humidity into the battery pack. When it comes to the cooling system, you need to be worried about over-pressurizing the cooling system. Putting too much flow rate through it or too strong of a pump can damage cooling systems. And then on the mechanical perspective, that you don't put excessive shock, vibration, and force into the battery packs that could cause mechanical damage. So there's many ways to mitigate these through both active and passive methods, and their protection systems are incredibly important to ensure the safe and long-term reliability of a battery pack. So that brings us to the end of our deep dive into safety systems inside of battery packs, battery modules, and some of the considerations to safely use and operate battery packs. Hopefully this was insightful. Thank you very much for watching.